Hello and welcome to another power system analysis class. I apologize. So in the last class, we started with power flow and different algorithms that we use for power flow and how we solve the current and voltage and how we solve power flow problems. And we use the Gauss method and we solve some problems on the iterations, and we solved some problems on two bus systems on Gauss method, using Gauss method. Now, if we have multiple bus, it's going to get more complicated with Gauss, and therefore we use other different methods as well. So let's see what happens when we have multiple bus systems and we want to calculate VI prime. If we want to do that, VI of V plus 1 is going to be 1 over YII SI conjugate VI conjugate minus the sigma from k equal to 1 to n YIK VK. In other words, it's going to be HI of V1 of V, V2 of V, until Vn of V. Now, but after determining the VI, V plus 1, we have a better estimate of its voltage, so it makes sense to use this new value. This approach for many bus is also known as the Gauss-Seidel iteration. We can use it to estimate the voltages, the new voltages as well. Using this method, V2 of V plus 1 going to be H2, V1, V2, V, V3, V till VNV. And H3 is going to be H2 of V1, V2, and of V plus 1, and so on and so forth. This method, the Gauss-Seidel method, and I will solve some problems, works better than the Gauss. It's easier to implement, but it has some drawbacks, and I would mention some drawbacks. Because it's easier to implement and it's actually a little faster, we replace Gauss method with Gauss-Seidel, and this one is the method that we actually use. Now, we have three types of bus flow buses. We have the load PQ, at which PQ are fixed. Iterations solve for voltage, magnitude, and angle. So P and Q are fixed. We solve for voltage and for angle, voltage, magnitude, and angle. And then we have a slack at which the voltage, magnitude, and the angle are fixed. Iterations solve for PX injection. So it's the opposite of PQ. And load PQ are fixed. We solve for voltage and angle. In slack, voltage and angle are fixed, and we solve for P and Q. And then we have the generator PV, at which P and V are fixed, and iterations solve for voltage, angle, and Q. So again, slack, load PQ, and generator PV. Load PQ is for load, generator PV is for generator, and slack is slack bus. And the generator, again, P and the magnitude of V are fixed. We solve for the angle and for Q injection. Now, special coding is needed to include PV buses in the Gauss-Seidel iteration, but they are not commonly used. So we would mainly focus on the load PQ and also the slack. So anywhere in the questions in the exam, if we mention a slack bus, means that the voltage, magnitude, and the angle are fixed, and iterations are solving for PQ injections. Now, another type of Gauss-Seidel convergence or algorithm is called the accelerated Gauss-Seidel convergence. In the previous method, Gauss-Seidel method, we're calculating each value of x using x of v plus 1 equals to hxv. In the accelerated convergence, we can rewrite this as x of v plus 1, xv plus hxv minus hxv. Now we introduce accelerated parameters, which is alpha. And you can see the equation change to this. Xv plus 1 is going to be xv plus alpha hxv minus xv. And here, if we replace alpha with 1, we get the standard Gauss zero. And larger values of alpha, we get the accelerated Gauss zero. And the problem with this, sometimes we may overshoot, we pass the convergence point. Now I'll explain, give you a little bit of example. But the advantage is that you get a much faster equation. Why? Because we have multiplied the weights, so we get to the answer, to the final convergence point sooner. Now, this is the previous example that we had and we solved. Now let's do the comparison of results with different values of alpha. On the left, we have alpha equal to 1. This is the normal Gauss zero algorithm here. And you can see that for k equal to 0, 1, we go from 2, 1 to 2 to 2.414, 2.5, 2.59, and 2.618, which is our convergence point. Now, if we put alpha 1.2, we get 1. Second one, we get a convergence faster, so 2.2, 2.539, 2.604, and 2.615. Okay, so we get to the answer quicker. And if we increase the alpha again, we get 1, 2.5, 2.6, 217, and you can see that we get to the convergence point or very close to that even sooner. But the thing is, if alpha is too high, we jump from 1 to 3. So we are overshooting. We're passing the result, and then we're going to get back to 2.64, You can see that we don't reach the convergence point as we intended. So this is a good solution if you want to have a very fast solution, but it doesn't give you the most accurate. That's the reason we get to the some advantages and disadvantages of Gauss zero, and these are the main reasons we no longer use them that much. So some advantages are that the Gauss zero advantages are that each iteration is relatively fast. The computational order is proportional to number of branches plus the number of buses in the system, and it's relatively easy to program. Disadvantages are that it tends to converge relatively slowly, although this can be improved with acceleration. It has tendency to miss the solution, as mentioned, particularly on large systems, so you're going to miss the solution, overshoot sometime. It tends to diverge on cases with negative branch reactances, common with compensated lines, if you have a capacitor bank. And then it needs to program using complex numbers. Now, and by the way, when you have 2, 3 buses, you can solve them manually with hand calculation. Imagine you have 300, 400, 1,000. It's like solving a 1,000 dimension problem. It gets super complicated. There's no way you can manually solve it. That's the reason we have softwares, programs that could easily solve these. Now, let's start with an example. We have a 2-bus system which has a slack bus voltage. So when we have a slack system, it means we know the voltage and the angle, and we're looking for P and Q. So load at bus 2, we have S2 is equal to 1 plus J.4 per unit. And using a flat start, V2 of 0 is going to be 1 plus J0. We want to find the first Gauss zero iteration for V2. And from the previous equations, for a PQ bus, the Gauss zero update is this. For the 2-bus system, it's going to be this equation here. Now, this is the same basic update structure presented in previous slides. Okay, I'll give you a few minutes to solve this, and then to think on this, and I'll start solving. Now, the first thing that we need to do, here in the equation, we have S conjugate, but in this problem, we have been given the S. So the first thing that we need to do is we need to find S2 conjugate. What is S2 conjugate equal to? Minus J.4 power unit. Is that correct? Yes? Okay. Now, for next step, since V2 of 0 is 1 plus J0, then V2 0 conjugate, because again, we have to find the conjugate here, is going to be equal to 1. Because again, the J is 0. So in this case, S conjugate of 2 over V2 0 conjugate is going to be equal to 1 minus J4. Because the denominator is 1, divide anything by 1, you get 1, the same thing. Now, we want to find, the next step is to find Y21 V1, because again, we have to find the sigma. So Y21 V1 would be equal to -5 plus J, because Y22 is 5 minus J15, Y21 is going to be -5, and already mentioned here, plus J15. So plus J15 times 1.04, which is our V1. Now, multiplying these gives us -5.2 plus J15.6. Okay. Now we want to compute the total, this bracketed term. Okay, we have already this is 1, and this is 2. So we want to compute 1 minus 2, the bracketed one that we have. So it's going to be, I'm going to write it like this, 1 and 2 combined is going to be 1 minus J4 minus -5.2 plus J15.6, which would be equal to 1 minus J.4 plus 5.2 minus J15.6, which gives us 6.2 minus J16. Now, what is the last step? We have to divide this by Y11, YII. So we would divide by, I did it step by step, Y22. So this is going to be equal to V2 of 1 would be equal to 6.2 minus J16 over 5 minus J15, which is Y22. Let me write that. Now, if we solve this, I already solved, you can multiply it by the denominator and then find it. You would get 1.084 plus J052. I've calculated this. So my final answer would be this. V21 would be equal to 1.084 plus J0.052 per unit. Now, if I want to convert it to the angle in the face, because we want to find the angle in the face, V2 of 1 would be equal to 1.084 almost, and V2 of 1 is going to be almost equal to 2.75 degrees. But usually in the complex form is good enough. Do you want to write it down? Did you write it down? Yes. Want to take a picture or you're done? Done? Yeah. So simply you just replace it in the equations and you find it for Vy2. We already did. Again, this is part 1, part 2, and then when we did it, we divided all part 3 by part 3. This is part 3, then we divide everything. Now, because of the disadvantages that we have with Gauss, the Gauss-Seidel algorithm, we use another algorithm called the Newton-Raphson algorithm, and this is the second major flow solution. And the key idea behind it is to use sequential linearization. And the general form of problem, we want to find an x such that f of x hat would be equal to 0. Now, the method is like this. For each guess of x hat and xv, we would define delta and delta x of v, which is going to be x hat minus xv. Represent fx hat by Taylor series about f of x. So fx hat is going to be fxv plus df xv over dx delta xv plus half of d square fxv over dx square delta x square plus the higher order terms. And usually we do it just for the first one. So approximate fx hat by neglecting all terms except the first two. The first two are the important. So if fx hat is going to be equal to 0, then this equation would be equal to 0. And we use this linear approximation to solve for delta x. Therefore, delta x of v is going to be negative df xv over dx inverse fxv. Now we solve for a new estimate of x hat, which is going to be xv plus 1, which is delta x of v plus delta x v. Now, I think showing a graph like this gives you a better visualization and an idea how the system works. So the system, you can see that we want to converge and reach the solution, okay? And the way that we do it, the derivative, what does the derivative do? Finds the slope. So when we find the slope, we find the point that slope is colliding with the x-axis, and then that's going to be our next starting point to find it. And we continue that until we reach the delta x or dx becomes 0. Sometimes we have multiple solutions. Sometimes we don't have solutions, depending on the equation that we had. We're going to use the same example that we had for the Gauss-Seidel, the Gauss iteration algorithm and convergence one. And let's see how many iterations it takes. So using the Newton-Raphson to solve fx, it's going to be x squared minus 2 is equal to 0. The equation we must iteratively solve is delta x. Again, the equation is negative df xv over dx inverse and fxv. So what is the derivative of this equation? It's going to be what? 2x. And since we have inverse of here, it's going to be 1 over 2xv. So a negative 1 over 2xv. And then fxv, what is it? It's going to be xv squared minus 2. Now xv plus 1 is going to be xv plus delta xv. We already found xv. And then we will replace it with this. And then we would solve, we would start with a guess of x0 is going to be equal to 1. Same thing that we did. This is already given. And then we iteratively solve. And we get for xv is going to be equal to 1. And then second is going to be 1.5, 1.41. 1.66 and 1.41422. And fxv, you can see how it changes, and you see how quickly we get converged to the final solution, which is at 2. For the previous one, it took 4 or 5 iterations. But this one, imagine you have a, and this is the actual graph. This is actually how it works. So when this goes, the slope goes to infinite, you just need to have 1 or 2, iterations to get to the answer. It's very, very fast. So at each iteration, the Newton-Raphson method uses a linear approximation to determine the next value for x. The function is fx of x squared minus 2 is equal to 0. The solutions are points where fx intersects with the fx equal to 0 axis. So the intersection that we have with the x-axis, that's going to be the answer that we're going to have. That is going to be here. Now, let's solve it for x2 minus 5 equal to 0. I'm going to give you a few minutes to think on this and solve this, and then I'm going to solve it. So use the Newton-Raphson to solve x squared minus 5 is equal to 0. And the first starting point is going to be x0 is going to be equal to 2. And if you want to take a picture from the equation, again, it's a very simple equation. And technically this delta x is f of x v, the v iteration, over, and by the way, it's negative because we have a negative. So it's going to be fxv over f prime of x v, which is the derivative, okay? So technically delta x is negative fx over Did you write down the equations? Can I go to the question slide again? Yes. Okay. Or I can even copy this here. Just give me a second to see if I can copy it. No, unfortunately, I'm not able to copy it. I'm gonna just write it down. So x of v plus 1 v. So it's going to be x v. And this is how actually it's written in the book as well. Make it simple. Do you want me to solve it? What do you get? Perfect. 2.236, yes. Now, so fx is x2 minus 5 equal to 0, or x2 minus 5. So what is f prime of x? It's going to be 2x, or the derivative. So x of v plus 1 is going to be x of v minus fx v over f prime x v. So therefore, if I want to find x1, it's going to be x of 0. And what is x of 0? So it's going to be 2 minus 2 and the power of 2 minus 5 over 2 times 2, which gives us 2.25. So this is the iteration number 1, or the first iteration. I'm just going to call the second one I2, or the second iteration. The second iteration is going to be x2, which is going to be x1. What is x1? 2.25 minus 2.25 in the power of 2 minus 5 over 2 times 2.25, which gives us, what did you get? I got 2.23611. Now iteration number 3, x3 is going to be equal to 2.3611 minus 2.3611 in the power of 2 minus 5 over 2 times 2.3611. And the answer for this one is going to be equal to 2.23607. So the third iteration, we have 2.3607. Thank you. Remind me to give you an extra point on the next. Now let's solve now that you did it, small quiz. Again, this is for just attendance mainly, but the portion would be also given. So question, you're gonna have 2 quiz questions. Number 1 is that same thing that we had in the previous question, but now x10 minus 10 is 0 and x0 is 3. I will give you 10 minutes to solve. I can zoom in a little bit. So. And we want the first three iterations. Again, for Newton-Raphson, we usually get to the answer in the 3 or 4 iterations, unless it's a very complicated, system. you find it, Tyler? What is it? Let me double check. Yes. Did you all solve it, or do you want me to? Okay. So f prime, we do it with different color. F prime of x is going to be again 2x. Now x of b plus 1 going to be x of v minus x2 minus 10 over 2x. Now for x1, we have 3, because x0 is 3. So 3 minus 9 is 10 over 6, which gives us 3.1667. So for iteration 2, x2, we have 3.16667 minus 3.16667 in a power of 2 minus 10 over 2 times 3.16667, which this one gives us 3.16228. And the third iteration, x3, is going to be equal to 3.16228. And you can already see that we are converging pretty fast. Minus 3.16228 in a power of 2 minus 10 over 2 times 3.16228. And if we calculate this, we get 3.16228 again. So you can see that we have already converged at the second iteration. Okay, so fourth, fifth, it's going to be the same. So the answer is 3.16228. Now, some comments about the Newton-Raphson. When close the solution, the error decreases quite quickly. Method has quadratic convergence. fxv is known as the mismatch, which we would like to derive to 0. The stopping criteria is when fxv is smaller than epsilon. So it's going to be very small number. Results are dependent upon the initial guess. What if we had guess x0 of 0 is 0, or x0 of 0, x of 0 is going to be -1. Sometimes if the initial guess is greater than the final answer, you're not going to converge. You know what I mean? So initial guess is very important. Again, we want to get to that converging point. If our initial guess is here, good. If it's here, it's even better. But if it's here, then it's not good at all. Okay, you're not going to get to your answer. So initial guess to the convergence is very important. So if our initial guess was around here, we would have few less iterations. Okay, again, if it's here, then you're not going to get to the answer at all. Now, a solution's region of attraction, or ROI, is a set of initial guesses that converge to the particular solution. The ROI is often hard to determine. Now, let's solve a problem example from a Slack bus. So a two-bus system has, the bus one has a slack bus of V1 equal to 1.04 with a degree of 0 degree. And the bus 2 is a PQ bus. Specified load is P2 is negative 0.8 P per unit, and Q2 is negative 0.3 per unit. At the current iteration, calculated powers are P2 of calculated power is going to be negative 0.5 per unit, and the Q2 calculated is going to be negative 0.1 per unit. We want to find delta P2 and delta Q2. I'll give you a few minutes to solve this, and then I would solve it. Again, we only want delta P2 and delta Q2. So since just we want delta P2 is the P2 specified minus the P2 calculated, which is going to be negative 0.A minus negative 0.5, which gives us negative 0.3. Same thing we do for delta Q2. It's going to be Q2 specified minus Q2 calculated. This is calculated, which gives us negative 0.3 minus negative 0.1, which is negative 0.2. It said as easy as that. Since we have time, let's solve another one for Newton-Raphson. And would make it a little more challenging. Just give me a few seconds to come up with a just give me 1 second. I'm looking from the solved problems on the book to see if find another one. Okay, this one is good. So we want to use Newton-Raphson to solve x3 minus 8 is equal to 0, and x of 0 is equal to 3. So our initial guess is 3, and x3 of minus 0, 8 is 0. We want to find the first 3 iterations. So find the first 3 iterations. Again, I'll give you like 10 minutes. Solve this. So keep an eye on your announcement. I'm going to announce some important things on your Blackboard, I'm sorry, Canvas. What do you get? Okay. Okay, let's start with the equation. The equation is going to be x v plus 1, going to be x v minus x3 minus 8, which is fx over 3x2. F prime of x is 3x2. 3x squared. Now, x1 would be x0, which is 3, minus 3 in the power of 2, which is 9 times 3, which is going to be 27, minus 8 over 27 gives us x in the power of 3 is going to be 27. So it's going to be 3 minus 19 over 27 gives us 2.293 or 630. 630. Now this is the first iteration. The second iteration is going to be 2.29630 minus 2.29630 in the power of 3 minus 8 over 3 times 2.29630 in the power of 2, which is almost going to be equal to what I had is going to be 2.2960 minus 0.25978, which gives us 2.03652. Now the third iteration is going to be equal to, or x2, third iteration is going to be equal to 2.03652 minus 0.445, or let's do it this way. Don't jump to the conclusion. So minus 2.03652 and the power of 3 over 3 times 2.03652 and the power of 2. The denominator is minus 8. So it's going to be 2.03652 minus 0.445 over 12.4444. And I'm going to write the result here, which gives us 2.00076. This is what I got. If it's close to yours. So the answer is 2.0003076. Okay, that's it for today's class. If you have any questions, just please let me know and keep an eye on your Canvas for announcements. Thank you so much.